Section 13.2, Acid Strength. Acid strength, an introduction. The strength of an acid is defined by the equilibrium position of its dissociation. In a strong acid, equilibrium lies far to the right, so our products are going to be favored. We're going to make a lot of H+. Almost all of the original HA is dissociated or ionized at equilibrium. It's called ionized because what are you doing? You're taking something that's neutral, like HCl, and you're splitting it up into ions, H+, Cl- at equilibrium. It's going to yield a very, very weak conjugate base. So, good rule of thumb, the stronger your conjugate acid, the weaker your conjugate base. So HCl is a strong acid, but Cl-, my leftover conjugate base, is a weak conjugate base. It can be described as an acid whose conjugate base is a much weaker base than water. Here's something that I want you to memorize. This is our list of strong acids. These are the ones that are going to completely dissociate, and there's not that many of them. All right, so up here we've got hydrochloric, hydrobromic, hydroiodic acid. These three together are going to be the hydrohalic acids, HX. All right, then we've got nitric, chloric, and perchloric. Those kind of go together. And then sulfuric. So when we think about sulfuric acid, it's H2SO4. It's got two ionizable protons. Only the first ionization is complete. It's still a strong acid, a pretty strong acid, but HSO4- is technically a weak acid. So all of these guys up here, right? Memorize these. It's going to make your life a lot easier if you know what your strong acids are, right? What is not a strong acid is HF, right? HF is not a strong acid. HF is a weak acid, right? Right, so it also helps to memorize that is not one of your hydrohalic acids. We'll talk about why a little bit later on. When it comes to your strong bases, these are your strong bases. Right? Lithium hydroxide, sodium hydroxide, calcium, rubidium, cesium. Notice these are all group 1 metals, right? Remember the name for group 1 metals. These are the alkali metals. Alkali means basic, so they are base forming. So if I take lithium hydroxide, it's going to dissociate into lithium plus, which is neutral, and OH-, which is the definition of what makes something a strong base for a Bronsted-Lowry base. Your group 2A, these are your alkali earths. You've got calcium hydroxide, strontium hydroxide, and barium hydroxide. And calcium hydroxide really shouldn't be on here as an analytical chemist because it doesn't completely dissociate. To the extent that it does, it's going to give you 2 OHs for every 1 mole of calcium hydroxide. And knowing that these guys are strong bases often shows up in kind of trick questions, right? So know that these guys are strong bases. Again, memorize these. It's not a lot to memorize, right? Group 1 and an OH. Group 2, for the most part, and an OH. But you need 2 of them. Right. Let's look at our acid strength again. So a weak acid, equilibrium lies far to the left, right? Most of the acid originally placed in the solution is still present in its conjugate acid form. So if you have acetic acid, something like 98% of it is still acetic acid with that proton stuck on it. 2% of it is going to dissociate and form acetate and hydronium. Most of the acid originally placed in the solution still present in that HA equilibrium. It's got a conjugate base that is much stronger than water. So acetate is a stronger base than water is. The weaker the acid, the stronger its conjugate base. That's another one of those concepts that you want to keep in mind as you're going forward. Right? So if you've got a very strong acid, you're going to end up with a relatively strong or relatively weak conjugate base. So HCl is a strong acid, but Cl- isn't going to change your pH at all. So something like sodium chloride, not going to change your pH. Right? The weaker you are as an acid, the stronger you are as a conjugate base. So let's take a look at this. So if I take something like HA and I let it dissociate for a strong acid, I'm pretty much going to end up with complete dissociation, right? My H's and my Cl's so totally separated over here on the left, right? For a weak acid, right? So something like acetic acid, right? I'm starting off with H and then acetate. I'm going to keep most of it, right? Not much of a change over here. I'm just going to form a very tiny amount of my H plus hydronium in solution and a very tiny amount of my conjugate base acetate in solution. So how do you describe acid strength? The easy way to do it is with your Ka value. Right? For a strong acid, your Ka is effectively infinite. It's very, very, very large. For a weak acid, Ka is small. It's less than 1. So typical values are going to be like 1 times 10 to the minus 4. Right? So very, very small values. You could think of it as the position of the ionization equilibrium. So Ka is large. It means you're going to go far to the right, far to the products. All right. In a weak acid, your equilibrium position is far to the left. It's going to favor your reactant side. You could look at the equilibrium concentration of H plus compared with the original concentration of HA. So in a strong acid, your H plus concentration and your strong acid concentration are about the same. In a weak acid, your concentration of H plus is much, much less than that of your conjugate acid. You could look at the strength of the conjugate base compared to that of water. So your A minus, your conjugate base, like Cl minus or Br minus, are going to be a much weaker base than water, right? They're not going to change pH at all. And A minus is much stronger base than OH minus. So something like, ammonia or something like acetate, right? Or phosphate or carbonate. Right. Here are our common strong acids: sulfuric acid, which is a dehydrating acid, perchloric acid, nitric acid. Some common weak acids would be phosphoric acid or nitrous acid or hypochlorous acid. So this is one that will trip people up a lot. Nitrous, HNO2, compared to nitric, HNO3. So don't let that nitric you. Right. We have a lot of different acids out there. We've got oxoacids. That's an acidic proton attached to an oxygen atom. So this is going to include your common strong and some weak acids. You've got organic acids that have a carbon atom backbone. It's usually going to contain the carboxyl group, this one, right? Where this proton here is the labile proton that's able to dissociate and go into solution. Your hydrohalic acids, HX. And the acidic proton is attached to a halogen, right? Where X represents something like chlorine or bromine or iodine. The bigger you are, the stronger the acid it is. So HI is going to be a stronger acid than HCl. And HF, which is teeny and tiny, is going to be not even a strong acid at all, right? Because it's not going to dissociate much. And why is it not going to dissociate? It's because of Coulomb's law, right? So I've got a very small area into which I'm packing that full minus charge of fluorine, right? That proton doesn't want to go anywhere, right? The charge separation, D, is small. So you're not going to give up your proton very easily if you've got a fluorine sitting right there, which is going to hold on to that charge on that proton. So it's going to keep that proton close. If the proton's being kept close to the fluorine, it's not able to go out in solution and form hydronium. It's going to make it a weak acid. Let's look at some of those organic acids. Acetic acid is one you will see a lot. It's got 2 carbons and then this oxygen, an oxygen here, an oxygen here, and then that acidic proton. Benzoic acid, right, like potassium benzoate or sodium benzoate to retard spoilage. Right? You'll see that a lot in food products. This H plus goes away. That's your labile proton. And then you can throw in something like, if it's potassium, you're going to put in a K, like potassium benzoate. Right? So benzoate is the conjugate base of benzoic acid. Right? We have a table for a K or a Ka table for a lot of common monoprotic acids. So HSO4 minus is going to be times 10 to the minus 2. Something like HF is times 10 to the minus 4. Something like phenol times 10 to the minus 10. That's something like nitric acid is going to be in the 4s. Acetic acid is into the minus 5s. Right? So you're having a rough idea of where these come in. Right? This HSO4 is pretty strong compared to acetic acid. Right? 3 orders of magnitude difference. Right? The units on Ka are usually going to be omitted. Right? So the bigger the number, right, the more you're going to do HA dissociates into H plus. The bigger the K, the more you favor the products. The more products you've got up on top compared to the reactants, the more protons you put into solution, the stronger you are as an acid. Right. Relative base strength is going to go something similar, except that you're going to look at whichever one has the smallest Ka value is going to be your strongest base. So phenol, this guy's going to be your strongest. And this guy up here is going to be your weakest base. All right. So note that this is only going to give you Kas. And what we're going to see is that you can calculate a Kb. So a Kb is going to be calculated by taking your base producing hydroxide in a reaction with water and then the conjugate acid. But for ease of use, we're only going to calculate or tabulate Ka values, because as we're going to see, there's a very easy way to go between a Ka and a Kb. So they're just going to list out Ka values, and then you can calculate Kb values. Yep. So there is a relationship between Ka and Kb for a conjugate acid-base pair. Our Ka is when we're going to take our weak acid and we're going to let it dissociate into H plus and the conjugate base. And for Kb, we're going to react a base, say A minus, and we're going to form hydroxide and our conjugate weak acid. Right. If I take these two and I multiply them together, right, remember our Ks are going to add. What we'll see is that our HAs will cancel out, our A minuses will cancel out, and we're left with just H3O times OH minus. And we're going to give this guy a special K value, Kw. And that W stands for water. Right? Because this is the expression for what's called the autoionization of water. So if you let water just hang around by itself, what will happen is that the water will spontaneously, two waters will come together and they'll spontaneously for a split second form both H plus and OH minus. And that Kw value, we're going to see how to use that in a second. So our solution. So water is a stronger base than the conjugate base of a strong acid, but weaker base than the conjugate base of a weak acid. This leads us to the following order. Cl minus is less than H2O, which is less than the conjugate bases of weak acids. So the weakest bases are going to become the strongest bases. By recognizing that the strength of an acid is inversely related to the strength of its conjugate base, the remaining conjugate bases can be reordered. So our Ka for HF is bigger than our Ka for HNO3, which is bigger than our Ka for HCN. So our base strength is going to be that F minus is less than NO2, which is less than Cn minus. So the combining those two orders in terms of base strength, Cl minus, which is the conjugate of HCl, right, which is a strong acid, is going to be less than water, which is less than fluoride, which is the conjugate of HF, a weak acid, which is going to be less than nitrite, which is less than cyanide. Water is the most common amphoteric substance. Amphoteric means that it can behave as an acid or as a base. The ion product constant or dissociation for constant or autoionization constant for water, that's that term Kw we saw before. And what it is it's going to be when two water molecules get together and you're going to form H plus and OH minus. So in pure water, we'll have an H2O and another H, and they'll give us H. and OH minus. And because these two waters are pure liquids, the only thing we have are H plus and OH minus in our product. So our K is just going to be H plus and the OH minus, right? And we'll give that special subscript KW because it's for autoionization of water. And in pure water, when we look at those, the concentration of H plus is going to be 1 times 10 to the minus 7 molar, and the concentration of OH minus is going to be 1 times 10 to the minus 7 molar. So at 25 degrees C, if we take our concentrations and we plug them in, we have 1 times 10 to the minus 7 times 1 times 10 to the minus 7, or 1 times 10 to the minus 14. And this times 10 to the minus 14 is going to be important. Some of you guys might already be familiar with the pH scale, which is going to range from 1 to 14. And if you're wondering why 14, that's a kind of arbitrary number to have a scale stop at, boom, it's right there, right? That's why pH scale goes to 14. Right? So let's review. I'm using KW. In any aqueous solution at 25 degrees C, no matter what it contains, the product of H plus and OH minus is always going to be equal to 1 times 10 to the minus 14. Why is that? Well, even if I throw in a strong acid, I've got, let's say, 1 molar HCl. And I put that in 1 liter of water. Well, my concentration of H2O, in terms of moles per liter, is going to be something like 55 molar. So even if I've got a strong acid, the main component in there is water. And that KW for the water is going to be the term that dominates how much H plus I've got and how much OH minus I've got. And so if you throw in something like H plus from HCl, it's still going to try to reach that 1 times 10 to the minus 14, but it's going to do so by decreasing the amount of OH minus I've got. So in a neutral solution where H plus is equal to OH minus, and in an acidic solution where H plus is bigger than OH minus, or in a basic solution where OH minus is bigger than H plus, those are 3 possibilities. No matter what we're doing, whether it's acidic or basic or neutral, my product of H plus and OH minus is always going to be equal to KW, because I just have so much of it, 1 times 10 to the minus 14. Right? So that product is always going to be the same. So what is the equilibrium constant expression for an acid acting in water? We've got HA reacting with H2O, and it's going to form H3O plus and A minus AQ. Right. We write out our K expression for that. We're leaving off this water. If the equilibrium lies to the right, the value for Ka is large or bigger than 1. If the equilibrium lies to the left, the Ka is small or less than 1. So let's do a quick concept check. If water is a better base than A minus, do the products or reactants dominate at equilibrium? Pause. What do you think? Products or reactants? Right, it's going to be the products. Right. Does this mean HA is a strong or a weak acid? It means that it's going to be a strong acid. Is the Ka value greater or less than 1? It's going to be greater than 1 because it's going to favor those products which include the acid. Right? Let's consider a 1 molar solution of HCl. Order the following from strongest to weakest base and then explain. So at 16 degrees C, we know that our concentration of H plus and OH minus are going to be 1 times 10 to the minus 13. So if we take X as both sides, right, set up an ice table just like we would with anything else, we're going to gain some H plus, we're going to gain some OH minus, so that we'll end up with X squared is 1 times 10 to the minus 13. We'll take the square root of that, and that'll be X, which will be our concentration of OH minus and our concentration of H plus, and they'll both be 3 times 10 to the minus 7 molar.